Now that we can draw Lewis structures for a variety of different molecules, what can we do with them? Well, one important job that we can do now is to predict the shapes of molecules. The shapes that the molecule has are pretty important in understanding how it works in biological machinery. Biological machinery very often contains some molecule with an active site, which is like a keyhole. And a molecule can come in and, because of its shape, fit exactly into that keyhole, flex it, and unlock some sort of a biological response. For example, if you smell something, there are keyholes in your olfactory receptors that can fit that molecule in and cause a response, a nerve impulse that is the smell that you perceive for that. If with an enzyme, a key can come in and fit into the lock and cause a chemical reaction to occur. A reaction that would not occur without the enzyme, without this lock and key mechanism working. To understand a lot of biology on a molecular level, you'll need to study this lock and key mechanism, and a big piece of it is, why is the key shaped the way it is? What kind of molecules will have the same shape? Can I forge keys to unlock locks? For example, if I want to make a pain relief drug, can I forge a key for a pain relief receptor? So this is kind of a fundamental thing for understanding all kinds of stories in biology and understanding all kinds of jobs that we might want to understand that have to do with drug activity, with hormones, with neurotransmitters. And this is the beginning of that story, being able to predict the shape of a molecule. Now, how do we take a Lewis structure and turn it into a shape prediction? Let's look at a couple of simple Lewis structures. Let's look at, let's say, a CO2 molecule. And I'm going to just draw the Lewis structures here. You've already seen the Lewis structures for these, built up step by step in earlier videos. If I have a CO2 molecule, and I want to predict its shape, I'm going to focus on the central atom. Let's draw the central atom as though it's a sphere. Now, I can look at the double bonds that are coming out of the central atom here as electron clouds. Now, you might say, well, there's two electron clouds in there because there are two bonds, but there aren't really. They're really one cloud there because the oxygen and the carbon keep the electrons that are in the double bond pinned down in one place. So what I have there is sort of a cloud of electrons on that one side. Now, on the other side, I have another cloud of electrons. Now, how do I know that they're laid down in a line like that? Because electrons repel. Those two clouds are going to arrange themselves on the surface of the sphere here so that they are as far apart as possible. If this one is on the North Pole, that one would be on the South Pole. I guess I can draw this a little bit more simply, like that. There's an electron cloud here and an electron cloud here, and they are an angle, 180 degrees apart. I can call this a linear arrangement. What if I've got one of the ones that was in your last worksheet, BF3? Here's the Lewis structure that you should have gotten in that worksheet for BF3. How many clouds do I have around the central atom? Here's the central atom. Well, there'll be a cloud here, and I'm just looking at the clouds that are immediately around the central atom. I'm not looking at those fluorines. I'm not looking at the lone pairs on the fluorines. I'm just looking at what's hooked up directly to the central atom. I can draw that shape a little bit more cleanly like this. Now, this is the way that you can arrange them so that they are as far away from each other as possible. If this thing is a sphere, all three of these things are flat around the equator, and they've got an angle of 120 degrees between them. How do I know 120 degrees? Well, it's 360 degrees around a circle. It would be a circle all the way around, and if I cut 360 degrees into thirds, I get 120 degrees. So I get a 120 degree angle there. This shape has a name. It's called trigonal planar. And it's called trigonal because of the three arms on there, and it's called planar because the arms and the central atom are all in the same plane. Now what if I do natural gas, CH4? My Lewis structure might look like this. Will look like this for CH4. How many things are around, how many clouds are around the central atom? 4. There are 4 bonds. Now, is that the way that I can arrange them so that they're as far apart as possible? Not really. If I allow these two to bend up out of the plane, they can be farther away from each other. So this is not the best arrangement that I have right here. It doesn't always look exactly like the Lewis structure that I draw flat on a piece of paper. There's a three-dimensional arrangement here that is better. Imagine that I have one cloud here and another cloud here, bent down a little bit more. They're not at right angles, really. And those are both in the plane of the paper. But I have one popping up out of the paper and one going back into the paper. This is how an organic chemist would write this shape, with a wedge for things coming out of the paper and a sort of a dashed line or a dotted line or a wavy line going back into the paper. What's the angle here? Well, it happens to be 109.5 degrees. And the name of this shape is a tetrahedral shape. So this molecule, because this shape in the center is tetrahedral, this molecule overall will be tetrahedral. And this, in a nutshell, is the way we're going to be predicting the shapes of molecules in this worksheet. And in fact, the three basic shapes that I have shown you, linear, trigonal planar, and tetrahedral, can describe almost all of the molecules that you are going to encounter in organic chemistry later on. These are the three basic electronic geometries. In the next video, we'll talk a little bit more about these electronic geometries.